Have you ever struggled to remember logic gates? Tired of having them thrown at you or swept under the rug? Irritated when people assume that you know what logic gates are and how they work? Or perhaps you just don't understand what your teacher's talking about? Well, fear not! In this video, you'll get all that plus more. Quite often, when you start to learn about logic gates, you get something called truth tables thrown at you, and you're almost expected to memorize that truth table. My goal here is to help you build an intuition of how to construct these truth tables on your own. I will certainly be using truth tables to demonstrate how these gates work, but I do not expect you to memorize these tables. For this video, all we care about is voltage levels. We don't care about other electrical characteristics such as current or resistance. Note that this is purely theoretical and that when you're constructing a physical circuit, you do want to keep those values in mind. Next is the truth table. The idea behind the truth table is to list all possible behaviors of a particular gate. Constructing a truth table is pretty straightforward. We put all the inputs on the left-hand side, counting up from 0, and the outputs on the right-hand side. I should note that this is the way it is traditionally done, but there's nothing stopping you from changing the order around as long as you have the correct output associated with the correct inputs. In effect, a truth table becomes a lookup table, but for simple gates, you won't actually need to look at the table. Lastly is the secret to all logic gates, the magic sentence, which is the output of whatever gate that you're looking at is true when input 1, the operator of that gate, input 2 are true. I'll explain how to use this sentence throughout the rest of this video, but this is how to construct any truth table you want without having to memorize the tables. This is the magic sentence. We'll start out with the buffer gate. Consider the simplified schematic. It's pretty easy to see what it does. When the switch is pressed, the circuit is on. When the switch is open, the circuit is off. Let's create a truth table of that. The switch has two possible states, off and on. Since we only have one switch, that means that there will only be two rows in our table. As we realized earlier, the output is going to be the same as the input. So let's substitute a 1 for on and a 0 for off. With this, we have built a truth table. But as I mentioned earlier, memorizing truth tables is not the best way to learn logic gates. Well, let's use our magic sentence then. We'll have to modify it a little bit since we are only using one input. The output of a buffer gate is true when the input buffer is true. Modifying it a tad more, the output of a buffer gate is true when the input is true. Now that we have a truth table, let's move a layer of abstraction up and replace the circuit with a symbol. We'll use a triangle here to denote a buffer. If you've dealt with analog circuits before, a triangle symbol will look familiar to you, and it should. Buffers are built primarily using op-amps. For pure digital logic, you won't find this gate particularly useful. I've only included it here to build a base for the next logic gate. So why does this gate exist? Without getting too much into it, a buffer allows us to source higher currents than what our logic inputs can provide. As we're focusing on voltage levels in this video, this is beyond the scope of this video. Next, we have the NOT gate, also known as an inverter. Instead of looking at a circuit first, this time we'll use the magic sentence. We again have to modify to use only one input. The output of a NOT gate is true when the input is not true. The little bit of information we glean from this sentence is that a NOT gate flips the output. Consider this circuit here. For the sake of simplicity, I've omitted the current limiting resistors, but just assume they are there. Notice that when the switch is open, or 0, the output is high, but when we close the switch, the output is low. This gate essentially does the exact opposite of a buffer, so let's give it a similar symbol. Note the little circle on the end. This will be important a little later on. Now we move on to the bigger logic gates. The buffer and the NOT gate both took a single input and output a result. The rest of our logic gates take two or more inputs and output a result. Our next gate is the AND gate. For this video here, we will stick to two inputs on our gates, but the same rules apply to gates with more than two inputs. Again, let's use the magic sentence. The AND gate is true when input 1 and input 2 are true. Let's construct a truth table. We now have the same number of states per input, but more inputs. A quick note if it hasn't made sense how I'm calculating how many rows I need in my truth tables. This is the equation right here, where x is the number of states, in my case 2, that the inputs can have, and n is the number of inputs. Plugging our numbers in, we have 2 squared rows, which is 4 rows. We won't go beyond 2 inputs in this video, but I wanted to point that out. Now we want to write down all possible combinations of inputs. Remember, position matters here, so 1, 0 does not equal 0, 1. Now that we've got our possible inputs written down, let's put our magic sentence into a truth table. Our magic sentence tells us that there's only one combination of inputs that yields an output true, and that is when both of our inputs are true. Now let's take a look at our simplified circuit for an AND gate. We'll try each of our combinations to see if the truth table matches. As we can see, we indeed only get an output high if both our switches are turned on. Now let's go up a layer of abstraction. We'll represent the circuit with this symbol. The 2 inputs are on the left, and the output is on the right. Next is the OR gate. Let's use our magic sentence again. The OR gate is true when input 1 or input 2 are true. Creating our truth table again, we can see that there are 3 rows that this sentence describes. Notice that here, there's only one position where the OR gate is false, whereas the AND gate was almost always false. Let's use a simplified circuit and see what's going on with an OR gate. As we test all the possible combinations, notice that it really only takes one switch to turn on the output of this gate. Now let's go up a layer of abstraction. We'll use this symbol here to represent an OR gate. Just like the AND gate, we have our 2 inputs on the left and our output on the right. Last of the gates is the exclusive OR gate, also known as the XOR gate. This one's a little trickier to remember, but we can use our magic sentence again. The XOR gate is true if input 1 exclusive OR input 2 is true. Let's modify the sentence just a little bit to make grammatical sense. The XOR gate is true if exclusively input 1 or input 2 is true. Another way to put this is, the XOR gate is true if input 1 or input 2 is true, but not both. Any of these sentences work? Just pick the one that's easiest for you. Let's make a truth table. With our inputs filled out, we just need to pick the combination of inputs dictated by our sentence. Our sentence tells us that we have to have an input that is high, but both inputs cannot be high. In our table here, there are only 2 combinations of inputs that fit that criteria. Notice that essentially, if your inputs are different, the XOR gate is on, and if they are the same, the XOR gate is off. A true XOR circuit can look rather intimidating, so I made a slightly simpler one here. Note that in this circuit, we are assuming that if a switch is drawn upside down, it just takes the opposite state of whatever is being input. Again, this is only drawn this way to illustrate my point. You won't encounter an XOR gate drawn this way out in the wild. Let's try all of our combinations and see if our truth table is accurate. As you can see, turning one input on will result in a high output, but turning them both on results in a low output. Now we go a layer of abstraction up from here. We'll represent this circuit with this symbol here. This is almost the exact same symbol as the OR gate, with the exception of this line. XOR gates are particularly useful for math and digital circuits, but that is also outside the scope of this video. Now you may have noticed that a little bit ago I said that XOR is the last of the gates. That is only partially true. We actually have 3 more: NAND, NOR, and XNOR. The N in these gates stands for NOT. Essentially, this is how we can represent these gates. All we do is invert the output of the respective gates to give the output of these new logic gates. Drawing a NOT gate after every logic gate can be quite a pain though, so we're going to shorten it. Remember that circle I mentioned earlier? That circle means to invert the signal. Using that, we instead get these symbols. Another note is that we are not limited to putting the circle on the output of a gate. We can also put it on any number of inputs into the gate. The name of the gate does not change, but its truth table does. I'll leave that as an exercise to you to figure out how though. Thank you for watching through to the end. I hope that you learned something. I repeated this magic sentence over and over and over again in the hopes that it can help you construct your logic gates, and much more importantly, give you an intuitive understanding of what is going on in the various gates. If you found this information useful, be sure to let me know down in the comments. I enjoy making this type of content and feedback is really helpful. Have a good rest of your day and good luck in your endeavors.